Welcome back everyone to the third part on my semi-course on Semiclassics. Today I would like to talk about some of the basic ideas, tenets and assumptions that underlie semi-classical approximations. To simplify the presentation a little bit, I will start with exposition of semi-classics of ordinary systems on RD. So with ordinary, I just mean I'm not looking at systems that have an underlying periodic structure or so. It's just something like minus Laplace plus potential. So kinetic energy plus potential. There's no additional periodic potential. So the first person to make these ideas rigorous, that was Ehrenfest. In the very beginning, in the early time of modern quantum mechanics in 1927, he wrote a beautiful less than 3-page paper. So it's the basic ideas are actually on the first 2 pages, not even 2 pages. The last section is dedicated to Gaussian wave packets, where he explains how to make his ideas rigorous for a particular type of wave packet. So it's very condensed. It contains all of the essential ingredients, and it only has a single flaw. And that is the paper is written in German. So of course, at the time, German was more widely read among the scientific community, but nowadays the lingua franca is English. So for the benefit of my listeners, let me give you the core of Ehrenfest's argument. So to do this, let me draw an illustrative picture. So let me start by drawing the potential. So I'm assuming that the potential looks something like this. And now let me add a wave packet on top of this potential. So here you have the envelope, and inside the wave packet you have a lot of oscillations. So you see that, let me call this wave packet psi of t and x, so it may depend on time. And what you can do is you can compute the de Broglie wavelength. And I claim that this de Broglie wavelength, or if you want, you can also take the basically the size, the approximate size of the wave packet. But you can also take something that is of the same order of magnitude. So the de Broglie wavelength is 2 pi h bar divided by the momentum expectation value. So this fixes the microscopic length scale, and just visually speaking, and again the definition need not be exact, but roughly you can also eyeball a macroscopic length scale, which is, let's say, roughly the distance between this local maximum and this local minimum, right? So Again, we can quibble about the exact lengths here, but this is an order of magnitude argument. So this is not so much about the exact numerical values. So what I'm proposing here is you introduce a semi-classical parameter and this semi-classical parameter epsilon, so I'm not using h or h bar on purpose, as I shall explain in a second. This is just the ratio of the microscopic length, characteristic length, divided by the macroscopic characteristic length. And for the red wave packet, this is less than 1. So and for general systems, I require that this is less than 1, that this is a small number. So to simplify this, let me color the numerator and the denominator in red and in blue, to emphasize that this is less than 1 for this particular choice. But of course, I could also draw a second wave packet. So let me just draw the envelope for simplicity. Let me call this phi here, phi of t and x. And you see that in this case, the characteristic length of the purple wave packet is of the same order of magnitude as the macroscopic length scale. So for this wave packet, you expect you do not expect a semi-classical limit to hold. So one of the important points, so of course the moniker semi-classical has yet to be justified. So epsilon is a small parameter, but it is not clear that this has anything to do with semi-classics. But this will come out at the end of the argument. One important point is that epsilon does not have units. In fact, all good small parameters must not have units. So this is because small parameters should quantify intrinsic relations between different components of your system or some such, but they should not depend on your units. So for example, h bar, which has units, cannot be a good small parameter. And that is simply because, depending on my choice of units, could be of the order of 10 to the minus 60. It could be equal to 1, which is indeed what most mathematical physicists do, so that they can get rid of it. Or I could also choose units so that it's 10 to the 80. So it is not a good small parameter. And then there's another point which is important, but it's, let's say, this is more of a claim that is illustrated by the next counterexample that I give. And that is that the potential V needs to be sufficiently regular. So regular means sufficiently often continuously differentiable, and the derivatives might have to satisfy certain additional conditions like boundedness or something like that. To illustrate this point, let me give you a counterexample. And that is the case where V is a potential, a step potential. So let me just assume I have a potential step that roughly looks like this, and that I have an incoming wave packet. Let me raise this a little bit. So the red wave packet is the incoming wave packet. And okay, if you have taken a course on quantum mechanics, then you know if if a wave packet hits a potential step like that, then part of the wave will be transmitted. Okay, that's not a surprise. But a part will be reflected. So this is after the collision. And the arrows on top indicate the direction in which the wave packets propagate. By the way, the height of the wave packet is supposed to tell you roughly the energy or the expected energy of the wave packet. And in this case, the expected energy lies above the potential step here. So quantum mechanically, you see what happens here is quite different from what happens classically, right? So classically, you would expect that if the particle's energy lies above that of the step, then what will happen is the particle will travel with one velocity up until it hits the barrier. Then it needs to pay a price and convert kinetic energy into potential energy. So it only has this bit of kinetic energy left. So it will still propagate in the same direction, but it will travel more slowly. But after it exits the potential step, it can convert the potential energy, so this here, back into kinetic energy, and it accelerates again to its initial velocity. So, but this is not what happens quantum mechanically. Here, the wave splits into two parts. And something similar happens if the wave, if the energy of the incoming wave packet is smaller than the size of the step. Classically, the particle will be reflected by the barrier, does not have enough energy to overcome the barrier. But quantum mechanically, you know that part of the wave will tunnel through the barrier. It's exponentially small, but it's non-zero. And so here you have a small transmitted part and a larger reflected part. So also here, initially you have a single wave packet that is split in two. And of course, the idea that Ehrenfest has with his wave packets is that the wave packet will remain a wave packet. So roughly speaking, he would like to identify the expected position, so the position average which is, let's say, if you zoom in, visually speaking, roughly here, I guess, he would identify this with the classical position of the particle. And this identification only makes sense if the wave packet remains intact. If it splits in two, this does not really work. So now you could ask yourself, well, but okay, here I also have a macroscopic length scale. So what's actually the problem? Well, the problem is that, okay, the potential might have a macroscopic size, but the derivative does not, right? So this is a step function. So the weak derivative of the step function will give you 2 Dirac deltas, and the size, so the prefactor of the Dirac deltas is proportional to the height of the step. And the Dirac delta is not slowly varying in any way. So what's the difference here? Well, between the step potential and this potential here, well, on the right-hand side for this potential, the length scale at which the potential varies is exactly the same length scale at which also the gradient of the potential varies. And that is the crucial part. And for this potential here, so roughly speaking, it's a sum of 2 deltas. I'm not writing the prefactors or the shifts. But the point is that this does not vary slowly. All right, so this gives us some initial hint and idea of what we can expect. Let us go and approach the topic from a slightly different angle. So let's say more from a conceptual angle. And that is physical systems are characterized by states, by observables, and by dynamical equations. And you can compare all of these ingredients for classical and quantum systems. And for the sake of concreteness, I've chosen a non-relativistic system, a non-relativistic spinless particle subjected only to something like an electric field. Then on the quantum side, you have the classical Hamilton function that gives you the energy of the system. So that's just 1 over 2m psi squared psi's momentum plus v of x. So kinetic energy plus potential energy. And similarly, in quantum mechanics, momentum becomes minus I gradient. So you have minus Laplace divided by 2m, where m is, of course, the mass plus the potential. This hat means that you're looking at the position, at the multiplication operator associated to the function v. In the Heisenberg picture, where you evolve states and keep observables fixed, the classical Hamiltonian equations of motion tell you how the point particle moves. Its solution is the classical flow. And on the quantum side, you have the Schrödinger equation. You can also, instead of evolving states, you can also evolve observables if that's your thing. That's the so-called Heisenberg picture. And here the equation for an observable on the classical side is given in terms of the Poisson bracket. So here I've just chosen the canonical Poisson bracket. And this, on the quantum side, the role of the Poisson bracket is played by I divided by epsilon times the commutator. So they look very similar, but on the quantum side, observables are self-adjoint operators. On the classical side, they are smooth real-valued functions. So you have some differences, but also some similarities. And now you have to figure out how to go from here, from the rightmost column to the leftmost column, right? And that's not completely obvious. Ehrenfeldt's solution to this problem was as follows. He just said, okay, for suitable wave functions, so for suitable states, I can look at expectation values of position and momentum. So here you have two, what I would call building block operators. So you have a position Q, of course I'm in the position representation here. Of course Q, if you're in d dimensions, this is in fact not a single operator, but a collection of d operators, which are just different components. And then you have momentum, which is just minus I gradient of psi evaluated at x, again on L2 over RD. I'm taking a little bit of liberty here because, of course, these are unbounded operators, so they're not well defined for all of L2 over RD, but each of these components, at least on RD, they only have a single sensible self-adjoint extension, and this is the operator that I'm talking about here. So I will not specify domains for simplicity. But another thing that takes a little bit of work to make rigorous, but is still intuitively clear, are the canonical commutation relations between position and momentum. So the different components of momentum, of position commute. Different components of momentum also commute. But if you look at position and momentum operator associated to the same fundamental direction, then this will give you plus I. So for the general case, you have to use a Kronecker delta. So now, okay, these algebraic relations also survive changes of representation. So here I'm in what physicists would call the position representation. Of course, I can also go to the momentum representation or any other representation I want. These algebraic relations between momentum and position operators, this is preserved. So one thing that is conspicuously absent so far is the semi-classical parameter, and this is not an accident. This was on purpose, because I would like to rediscover the epsilon in the course of the discussion. So and that means what I would like to do is I would like to work in the Heisenberg picture. So I evolve observables and keep states fixed. This is, of course, just a matter of personal choice, a personal preference. I can also do the opposite. I can work in the Schrödinger picture where I evolve states and keep observables fixed. This is completely equivalent. But the point is, I would like to choose, because epsilon is absent, rather than using the Heisenberg equation that I just showed you, I'm going to use the one where epsilon is equal to 1. So this is equivalent to, well, f of s is e to the plus ish, f e to the minus ish. So I just have to conjugate with the unitary evolution group. So another important point here is that I have chosen to relabel time. This is also not a notational accident, so I didn't just make an error here. So this here is the time variable. In fact, it turns out that this is the microscopic time variable, and I would like to keep t for the macroscopic time variable. So that's why I switched from t to s. Again, why this is so will become clear in during the discussion here. All right, and now I can look at expectation values. And then we're going to look at the time derivative of these expectation values. So expectation values of Q of S and P of S. And I'm going to denote them with small q psi of S. And they're the expectation value of the operator Q of S, okay? And this quantum expectation value is the scalar product of psi with Q of S psi. And if you write out the evolution, I'm missing a psi here, then you see that this here is psi of S. So again, psi of s solves the Schrödinger equation without the semiclassical parameter epsilon on the left-hand side. And when you bring this factor to the other side, this plus sign turns into a minus sign. And then you also have psi of s on the left-hand side. And so this is nothing but the expectation value of the operator q with respect to the time-evolved state. So in short, this equality here is just another way of saying that the Heisenberg picture is equivalent to the Schrödinger picture. I'm only writing this down in so much detail because we will use this argument in our derivation in just a moment. You can do the same for the momentum expectation value. Which evidently also satisfies relations like that. And now what you can do is you can compute the time derivatives. So the time derivative of q psi is the same as the expectation value of the time derivative of q of s for the state psi. I can plug in the Heisenberg equation of motion. So that's I times the commutator of h with q of s. And now you can exploit that h is a constant of motion, which means you can pull the time evolution out of the commutator, which means you can apply it to push it from the operators to psi. And then you're left with a time-independent commutator between the Hamiltonian and q. In our case, the Hamiltonian was the sum of two parts. So it was the sum of kinetic energy. So that's p squared divided by 2m commutator with q plus, well, now you have the potential term. But of course here, since v is defined by functional calculus with respect to the operator q, or the collection of the operators q, this here must be equal to 0, so the last term is absent. And a little bit of algebra tells you that this here is equal to p divided by m. So this here is the expectation value of p of s divided by m with respect to the state psi, which is the same as small p psi of s divided by m. So you just look at this here up to the factor 1 over m. M is the mass, so it's just a constant. You just arrive at this definition here, right? And this is perfect because this is the first component of the classical equations, of the classical Hamiltonian equations. Okay, nice. So what about the momentum coordinate? Let's do the same and see what happens. So I will not go through the same level of detail, but the basic steps are still the same. You plug in the Heisenberg equations. So let me just explain it here. You get this. You can again push the time evolution to the wave function. You can then split again into kinetic energy and potential energy. So let me pick off right there. So now we are here. So we have to look at the commutator of p squared divided by 2m and p. So clearly this guy vanishes, and the non-zero contribution is given by the potential. And if you compute this commutator, then you get minus the gradient of v of q. So this looks very, very good, right? I mean, we recover the gradient. Isn't that what we want? Well, not quite. You see, we recover the gradient in the wrong place in a way. Because this is the average of minus the gradient of the potential and that is different, and this is the central point. So unless the potential is quadratic, or more precisely a polynomial of degree less than or equal to 2. So of course if it's linear or constant, this equality is exactly true, but in general for all other potentials it will be false. This is different from minus the gradient of v of q psi of s, which you can also write as minus the gradient of v evaluated at the expectation value of q of s, of the operator q of s, or to write it yet another way, this minus the gradient of the expectation value of v of q of s with respect to psi. But the point is that the expectation value of the gradient of the potential is different from the gradient of the potential evaluated at the average position. So again, this is not equal unless v is a degree less than or equal to 2 polynomial. Okay, but this is, let's say, not 100% intuitive yet, I would claim. So let's summarize it and draw a picture. So when does a quantum system behave semi-classically? And I mean this in the context of the Ehrenfest theorem, of course. And the answer, well, let me write down the answer as an equation. That is when the derivative of the momentum expectation value, which we've just computed to be exactly equal to minus the expectation value of the gradient of the potential, if this is approximately equal, so the green approximately equal sign, that's the answer. If this is approximately equal to minus the gradient evaluated at the average position. Okay, but this is just rewriting what I just wrote down. So why don't we make use of this image here that I drew earlier? Just have to pay attention that it's not cut off by my beautiful face. So here we can already see why the purple and the red wave packet behave differently. So if we zoom in to the red wave packet, then you see that the gradient, so we're interested roughly in this region, and inside of this region, the gradient does not really change appreciably. So that means that the gradient of V across the wave packet where the amplitude is appreciably different from 0. So this is going to be determining the main part of the probability, the main weight. And because it's approximately constant, it is approximately equal to the value at the center of the wave packet, which is cube psi of S. So here, for this particular wave packet, it is correct that the gradient of V evaluated at the expectation value of the position is approximately equal to the expectation value of the gradient of the potential. Right? I mean, we just confirmed this visually. But if you look at the purple wave packet, then this is not true, right? So because let's say we're in this region here, the if we're in one dimension, then the slope is negative, and in this region the slope is positive. So it is not true that to say that, okay, I can just, let's say, take the expected value in position, which is roughly speaking here, which is 0, right? Because you will have a part of the wave packet that will be pulled in one direction and another part that will be pulled in the other direction. So it's not that easy. And here for the purple wave packet, these two are appreciably different. So for the purple guy, so this already gives us some insight because it explains why we need the regularity, right? Because it is the gradient of the potential that enters into the classical equations. And so what matters is the length scale on which the gradient of the potential varies and not the potential itself. But for some potentials, in particular smooth potentials, these two scales will usually be one and the same. So let's make some preliminary conclusions. Just to summarize what we've learned. The first one is that the gradient of the potential must exist as a function. And it should be locally bounded. So we don't want to have any singularities. So just to appeal to another example, one fundamental aspect of quantum mechanics is that it explains why the hydrogen atom is stable. So here it means that the energy spectrum is bounded from below, whereas the associated classical system is unstable because there's no lower bound on the energy, and that's because you have an infinite singularity. The second point is the variation of the gradient of the potential. Or let's say of V and the gradient of the potential. This must be slow when compared with the spread of the wave packet. So psi here is always a wave packet. And that means that the semi-classical parameter must be less than 1. And the last point is that it suggests that the semi-classical limit is only valid for wave packets. So let me just highlight the keywords to make it a little bit easier for you. So it turns out that this last suggestion is actually not true. But you would need a different technique. So for example, you can use Val calculus and Val quantization to prove semi-classical limits more broadly. All right. So let's translate what we've learned and put it into an iterated version of our model. And that is that we need to identify the relevant time and spatial scales. So as I said before, you start, and this is this assumption here, you start with a semi-classical parameter. And now we will rescale the potential. So we will do this by replacing v of x by v of epsilon x, where of course v is assumed to vary on a scale of order 1. So that means that v of epsilon x varies on a scale of order 1 over epsilon. So put another way, x is measured in microscopic units. And if we're putting ourselves in the position of an ant with our short legs, we will have to walk a very long distance to travel macroscopic distance. But this has also certain other implications. Namely that if we're looking at gradients, which are the fields, these fields must be order epsilon weak, right? Because if we take the derivatives, then the fields must be small. And so if we plug this into the classical equations, we need to wait long times to see an order 1 effect. So we need to wait long macroscopic times, which are again 1 over epsilon, to see order 1 effects. So this is quite important. So the last point I will make precise now. So I will have another look at this second argument and explain to you precisely how to translate this vague idea, this intuition, into mathematical equations. So let's identify the relevant scales using equations rather than intuition. So as before, we will include epsilon in the potential, and that suggests to use q epsilon as the position operator, which is just epsilon times q. And that changes the canonical commutation relations. Well, the first two are exactly identical because epsilon times 0 is equal to 0. But the last one is modified. So instead of being equal to plus I delta Jn, it's plus I epsilon delta Jn. So you just have to use the definition and use the linearity of the commutator in each of its two arguments, and that's that, right? The Hamiltonian, because we have replaced v of x by v of epsilon x, the relevant quantum Hamiltonian can now be briefly written as, and now I'm using the subscript epsilon. So that's just 1 over 2m p squared. It might be hard to read. Plus not v of q, but v of q epsilon. So the epsilon simply gets absorbed into the position operator. All right. So when we compute the quantum expectation values, if we include the epsilon, then, well, to indicate this, I'll write small q epsilon of s, epsilon psi of s, which is defined as the derivative of the expectation value of q epsilon of s. So here the this is still evolved according to the Heisenberg equation without the epsilon. So this is microscopic time, so there's no epsilon here. And now we can repeat the computation, but instead of being I would like to work smart and not hard, because q epsilon is just epsilon times q. This is the same as epsilon times the time derivative of the expectation value of the position operator without the epsilon. And we've already computed that. This is just epsilon times p epsilon psi of s divided by m. All right, so this here is of order epsilon, importantly, right? Because you have epsilon as a prefactor. So in this sense, the change of position, the velocity, is small. And similarly, you can define also the equation for the momentum. Then also here, what you get is simply, essentially, because of this here, you get an epsilon prefactor. So it's minus epsilon times the expectation value of P of S. Of the gradient of V of Q epsilon of S. And also this here is order epsilon. So now what we can do is we can introduce macroscopic time. And macroscopic time is defined exactly how you think it is. And this I will denote with T. T is just S divided by epsilon. So let's parse this real quick. For macroscopic time to be of order 1, microscopic time has to be of very, very large. So if I do just a tiny change here, then I get a large change on the other end.